Hi, Professor Baldwin here, and today we're going to talk about exponential functions and graphs. An exponential function is a function in the form a to the x, where x is a real number and the base a is greater than 0, and a isn't equal to 1. We're also going to look at Euler's number, which is e. And e equals 2.71, and it goes on and on and on. It's irrational since it doesn't repeat and it doesn't terminate. It's the base of natural logs, which we'll see in a few sections, and it's found in a lot of different areas of math. Well, let's look at how to graph an exponential function. You're going to graph an exponential function just like you would graph any other equation or even a line. Let's make a chart. So we're going to pick values for x, and we're going to find the corresponding y, or f of x value. We want to pick some smart numbers. Let's start with -1. -1 would be equal to -2 to the power of -1. Remember, an exponent that's negative puts that value into the denominator with a positive exponent. And 2 to the 1, or -2 to the power of 1, just stays itself. So this is -1/2. So we can plot this point, -1, -1/2. Now let's look at 0, because an exponent of 0 means that the base is just becomes 1. So 2 to the 0 is 1, but this is negative, so it's a -1. Because this is the same as -1 times 2 to the x. So we're finding 2 to the 0, which is 1, and we still have to multiply it by -1. So let's plot that point, 0, -1. Okay, we're getting a general idea of the shape. Now, what if we use 1? That's another easy value to calculate. That would be -2 to the power of 1. And anything to the power of 1 is itself, so this is -2. So 1, -2. Let's do one more point. 2 should be relatively easy. That would be -2 to the power of 2. Remember, this is the same as -1 times 2 squared, or -4. And that would be this point. So we see that it's going exponentially towards the negative y's on the right-hand side, and on the left, our graph is approaching 0. So there we've graphed f of x equals -2 to the power of x. Now, what if we have an exponent of x plus 1? Same thing. So we're going to make a chart, and then we're going to graph the function, and then we're going to explain how this graph could be obtained from a graph of a basic exponential function with different shifts or stretches, etc. So again, let's pick some easier values. Let's pick -1. Well, that would be 2 to the -1 plus 1, or 2 to the 0, which we know is just 1. So -1, 1. 0 would be 2 to the 0 plus 1, or 2 to the 1, which is just 2. Starting to somewhat see what it's doing. A value of 1 would be 2 to the 1 plus 1, or 2 to the 2, which is 4. Let's try one more, 2. This is 2 to the 2 plus 1, or 2 cubed, and 2 cubed is 8. So we see that it's growing exponentially in the positive y direction. And on the left side, it's approaching 0. Well, this is taking that basic function, y equals 2 to the x, and it has a plus 1 inside the function, so this is a shift left of that 1 unit. Right? You see how this graph has shifted to the left 1 based on how y equals just 2 to the x would look? Okay, let's look at an example using exponential functions. And this example is going to use compound interest. The compound interest function is a of t equals p times 1 plus r over n to the power of n times t. P is your principal, so how much you start with. R is your interest rate as a decimal. N is how frequently the money gets compounded, and T is the time. So our example, we have $82,000 invested at 4.5% interest, compounded quarterly. So 82,000 is our P, that's what we're starting with. 4.5% is 0.045. That's our R as a decimal. Compounded quarterly, this is our N, and quarterly means 4 times in a year, so N equals 4. We need to find the function for part A. So A of t would be equal to P, which is 82,000, times 1 plus R, 0.045, over N, which is 4, to the power of 4 times T. And we don't know the time. And we can simplify this. Principal stays is 82,000. 1 plus 0.045 over 4. Punch that into your calculator real quick, and this is 1.01125 to the power of 4t. That is our simplified function for how the investment grows after t years. Now we're going to find the amount of money in the account at t equals 0, 2, and 10. Well, when A of 0 times 0, we would have 82,000 times 1.01125 times 0 as our exponent. This exponent becomes 0, so this last piece becomes just 1. So at times 0, we have $82,000. That makes sense, right? Time 0 is when you first invest, and you're investing 82,000. Time 2 would be 2 years after investment. So we use that same function, except now our exponent is 4 times 2, or 8. You punch that into your calculator real quick. We can do this actually. So we have 82,000 times 1.01125 to the power of 8. And this equals $89,677. So $89,677. A of 10 would be how much money after 10 years. So 82,000 times 1.01125. Our exponent is 4 times 10. Let's plug that into our calculator real quick. So 82,000 times 1.01125. Use that caret key to get our exponent, and our exponent is 40. Hit enter, and after 10 years, we have $128,000. That sounds good to me. Okay, part C asks us to graph the function. Well, we're going to graph this function using our graphing calculator. So you pull up your graphing calculator and you need to go to the y equals. And then you're going to enter your function, which is 82,000 times, so we can do parentheses, 1.01125. We can close the parentheses. That value is to the exponent of 4 times x. And then we'll hit enter to save. And then if we hit the graph button, it's going to give us a graph. and we see that we have that exponential graph. Now, part D is asking, when will the amount of money in the account reach $100,000? This is another time that we can use our graphing calculator, because reaching $100,000 would be asking, when does A of t equal 100,000? Well, that would be taking our function and finding when it's $100,000. Or in graphical form, that's an intersection. So we have the graph of our compound interest function. If we go back to the y equals, we can put in a second graph for $100,000. We can hit graph and see it gives us that horizontal line representing the $100,000. And we can see that there's a point of intersection. Well, if we hit second and then trace, you see number 5 says intersect. Hit 5 and it's going to help you calculate the approximate intersection. You have to answer a couple of questions first. At the top, it's showing your equation, and at the bottom, it's saying, is this your first curve? Well, this is when I like to check and make sure that I actually entered my curve in correctly. I did, so I'm going to hit enter that yes, that's my first curve. Then we're shown a different equation and asked, is that our second curve? Yes, our second curve is 100,000, so I'll hit enter. Then it says, do you want me to guess? Yes, of course I want you to guess because I don't want to do that math by hand. So I'll hit enter. And look, it pops up the intersection. When y is 100,000, x equals 4.43. So x, or t, is 4.43. Well, time is in years, so this is 4.43 years, or just under 4.5 years, in order for that $82,000 to become $100,000. Not bad. Let's look at another example where we have to use our graphing calculator to help us find points of intersection. So here we have two separate equations. We're going to pull our graphing calculator back up. We need to go back into the y equals. If you have graphs in there, you want to clear those. And then we want to enter each of these equations. So the first one is y equals 2 e to the x is this blue function. So we have to hit the second button and then e. And notice that it gives us the ability to put in the exponent. So we'll hit x. Then you're still staying in the exponent area. So we need to hit the arrow to the right key in order to get us out of the exponent, and then we can do the -3, since that's not part of the exponent. Hit enter, and we can enter our second equation. That's y equals e to the x. So I am going to do second e, put the x, I'm going to arrow over, I'm going to hit division, and then another x. And then I'll hit enter. Then we can hit the graph button. Here we have our graph. It looks a little chaotic, but we can see that we have 2 points of intersection. And to find those points of intersection, remember we need to hit second, trace, and then 5 for intersection. Now it's asking, is this your first curve? Yes, that's correct. I'll hit enter. Is that your second curve? Correct. I'll hit enter. And now it's saying, do you want to make a guess? Yes, I do. So we'll hit enter. And notice that it's giving me a guess of this intersection on the right. And that value is x of 1.051 and y of 2.72. So let's write those down. So we have 1.051 2.722. But if we go back to that graph, notice that we have another intersection here on the left. So what we need to do is we need to arrow over and do that second trace again, 5 for the intersection. We need to move our point down the curve so that it's to the left of that other intersection point. And we're going to hit enter, that's our first curve. It's asking, is this our second curve? It is. Do we want to take a guess? Yes. And notice that now we have the intersection of that left intersection point. And it's negative 0.4022 and y equals negative 1.66. So let's write that down. So there you were able to use your graphing calculator in order to find the intersection of graphs. If you still have questions or you come across a problem you need help with, please leave it in the comments and I'll create a video for you.